So this part 2 is going to look at the case where how do I actually take any of these frequency domain conditions and put them in a better computational test which ensures guarantees without really checking for infinite number of things, right? There may be an iterative approach to check some feasibility of some of the inequalities, but beyond that you will get a guaranteed answer, right? So that's what we will look at it, and then basically the results, these are classical results that came for a different purpose and things like that. We will look at that purpose in the next lecture, but they are called as positive real and bounded real lemmas, and these were discovered not for robust control but actually something called sector nonlinearity we will look at later. Okay, so these are quite technical, but I'm going to state them and then make it as intuitive as possible, right? So let g of s be a square transfer function, something called analytic and real, positive real side of the imaginary plane. And let's not worry too much. Analytic simply means basically it has first derivative and things like that, which means it has all kinds of derivatives after that. It also means that one can actually expand the Taylor series, and analytic has a lot of story in it. For the timing, let's say it's a nice condition that we want it to be satisfied. And most of the transfer functions we deal in with regular systems will be of that form, right? So then we define g of s to be this property positive real if g of s plus its Hermitian part g star of s is greater than or equal to 0 on the side that where real part of the s plane is positive, right? We call this as strictly positive real if g of s minus epsilon is positive real. And there are many versions of positive real and things like that. There is something called strongly positive real, which we don't really talk about in this particular lecture, but there are many other versions of strictly positive real and things like that. There have been so many different papers because it's a very subtle topic and things like that, right? So then we'll get right into the result, which talks about how do I check positive realness of this particular thing. Just to remind you, basically, if something is positive real, it will automatically satisfy the typical frequency domain conditions we have. So in that sense, whatever we are going to have result basically becomes a sufficient condition for checking the frequency domain condition. And there are results that show that even though the definition is on the entire complex plane, one can actually just test things on the imaginary axis and things like that, right? So anyway, our purpose is to actually get away from frequency domain and come to the time domain. So let g of s to be the standard transfer function. Only thing, we'll assume that it's a square so that the size of input and output are same. So the delta becomes a square. One can develop for rectangular, but it's messy. So anyway, the fact is basically the positive real lemma states that a bunch of things are positive equivalent, right? The first statement is positive real. The second one is, if you have this input u, and then for that input you will get an output from this transfer function. Then if you take the integral of u transpose y, the inner product between u and y, for any length of time, basically it's going to be non-negative, right? So it's such a non-intuitive result at this point. For the time being, let's not worry too much because we're going to spend quite a bit of time on this particular condition in the next lecture and more general conditions than this, right? So anyway, that's nice to know that basically something is positive real is equivalent to this integral condition, but beyond that, not really much of interest at this time, right? But what is of interest is actually it's equivalent to this linear matrix inequality, which we know how to check, okay? So we just have to check for this positive definite matrix P such that this linear inequality where A, B, C, D are known, whereas P is something that we are checking. So of course, if we do find P, what it means is a separate issue, but for the timing, it's simply I can check some frequency domain condition through LMI, right? That's the purpose of this particular result. And actually, like I said, this was discovered much before people started looking at uncertainty systems, that the way we were looking at it. They happen parallelly for different purposes and things like that. There's a lot of rich history behind this particular series of results. Originally, these were discovered in Russia, and Yakubovich, for example, one of the first inventors of linear matrix inequalities, Popov later extended some of these results, and finally Kalman brought them to US and then actually presented the most general condition. And therefore, this result, not only it's called positive real lemma, but it's also called as KYP lemma or Kalman-Yakubovich-Popov lemma. And then there are many extensions to these things in nonlinear systems, which we will look at, right? Traditionally, these are written as equalities, but I chose to write as LMIs because that's the way we compute these days, right? So anyway, the summary of this particular result is, if you want to check some frequency domain condition like positive realness, and we can do so through this LMIs, right? So what about the strict positive real version? And basically the equivalent conditions are as follows, right? G of s is strictly positive real if and only if basically this integral u transpose y is greater than or equal to 0, except with basically an exponential weighting in front, right? And that's equivalent to this set of linear matrix inequalities. Okay. Now, I'm very fond of this particular result specifically because the connection to between the strictly positive real and then this integral is actually something that was part of my PhD dissertation, and this actually is one of the cleanest ways of looking at strict positive real functions, and provides the necessary kind of strict negativity in the v dot, the Lyapunov derivative that we typically have, right? And we will see some of these things at a later time. So what is the difference between positive real and strictly positive real? Well, if you remember, g of s minus epsilon is positive real is what it means for something being strictly positive real. It's positive real, but slightly away from that imaginary axis, and then that's equivalent to looking at some kind of u transpose y with an exponential this thing, but it has a almost similar, slightly more restrictive condition to ensure strict positive realness, right? So these are the positive real ones, and then you will have something similar called bounded real transfer function. These are historically very popular ones, and then they also have direct applications, so that's why we look at them separately. So what is something called bounded real? Well, it's very similar to positive real, except basically instead of g plus g star, you'll have I minus g star g. But other than that, it's the same thing. Strictly bounded real is same thing. And you have the corresponding version of strongly bounded real. Okay. And then you can imagine bounded real lemma, and it goes something like this, right? GS is bounded real if the integral of y transpose y is less than or equal to integral of u transpose u. It's like saying basically the input is always going to be greater than output in a size sense. U transpose u is like a square of the norm of u and things like that. So this again goes back to this thing called H infinity, if you're familiar. If you're not, we will discuss that at a later time. Basically, essentially bounded real systems guarantee certain size on the output compared to the input. So if you remember, we have spoken about bounded input, bounded output stability. One of the best ways to actually understand bounded output stability is through this inequality, and bounded real systems provide that, right? So, but of course, we also have the equivalent LMI, right? And the nice thing about this particular bounded real and positive real is they go back and forth. If somehow we know that g of s is bounded real, then we can do a transformation on g of s and then call h of s. And if you ensure that h of s is positive real, then g of s is bounded real and vice versa. So if you know one of these results, the other one comes for free, right? And you have the strict version, and again, the only difference is epsilon comes into picture everywhere, but beyond that, relatively straightforward, right? So anyway, like I said, a lot of these the bounded real versions will have strong connection to disturbance rejection problem, and then we will look at the disturbance rejection at a later time. It's very much intricately connected to robustness, right? Robustness is about, typically we imagine that to be unmodeled dynamics or unmodeled parameters and things like that. Disturbance rejection is more about some external noise coming in, and how do we sustain within that particular way, existence of the noise. And then one can imagine actually a block, again uncertainty sort of being a proxy for the disturbance rejection, and we will look at that carefully. So some of the robust control analysis results actually can include disturbance rejection through introduction of an artificial uncertainty. So anyway, all these things can be generalized in the following result, which says something like if this particular condition is true, and we're not naming it, let's, if you want to, we can call it as G is generalized positive real if this is satisfied for some matrix Q, R, and S. Then we have the following condition on Y and U, and then corresponding LMI, right? And you can imagine, basically, if I pick Q and R to be 0 and S to be identity, that becomes positive real. If I pick S to be 0, then R minus identity and Q to be, Q to be minus identity and R to be plus identity, then that becomes bounded real. So this particular result is kind of combination of both of these things and many more, right? And then this is the most general result. And again, this result, if we know, we can specialize to everything else, but you can actually prove this result using the positive real lemma and things like that. These are all equivalent in some sense. Some of them are more readily applicable to different scenarios, but this is the most general one, so this is good to have in front of us.